Okay. Welcome to our dynamic talk by Grid Dynamics. We are glad that you joined us today. Uh, so let's get to it. My name is Rakshita, and I will be moderating today's event. Welcome again to our dynamic talks by Grid Dynamics. Today our topic will be adopting design patterns for effective microservice architecture. This is the second event in the series of us talking about microservices and adopting them and the advantages and disadvantages. Before I start, I want to share some rules and tell you more about our company. So for the rules, during our talk, you can ask questions via the Zoom chat. Please check that the message in chat is visible to all participants. After the report, the speaker will answer them. At the end, you can also use your microphone and ask questions in the Q&A part at the end of it. Now, talking about our company, Grid Dynamics. So Grid Dynamics is a leading provider of technology consulting, agile custom software development, and data analytics for Fortune 1000 and Global 2000 enterprises undergoing digital transformation. Currently, we are in 18 countries with 4,000 plus engineers and architects and tech managers. Currently, we're also NASDAQ listed since the 2020. And we were found in Silicon Valley in 2006 with the mission to bring emerging technology to large enterprises. We have been a digital innovation partner for Fortune 1000 companies like Google, eBay, Microsoft. Even in the retail, we've worked with Macy's, we've worked with Raymond James in finance, and many more. Here is a QR code to our career site if you would like to see what are the openings right now, and if you would join us in our team. Moving on, I invite our speaker Chandra to take over, and he will be starting his presentation right now.
Thank you, Rakshita. Good morning, all. Good day. So I'm Chandra Kiran Donthoji. I'm working in Grid Dynamics as a staff software engineer. Today, I will be delivering a session on adapting design patterns for effective microservice architecture. So I composed the presentation based on my understanding and microservice patterns. Let me share my screen. Let me know once you see my screen.
Yes, we are able to see your screen, Chandra.
Yeah. Today, I will be delivering the session on adapting design patterns for effective microservice communication with architecture. So this is composed based on my experience and knowledge I gained on working on microservices. So let's continue with the session. So agenda of the student today's session is first we'll be looking at the overview of the microservices. And then we look at common challenges while building the microservices. And we'll try to understand the importance of the microservice patterns, and we explore some of the microservice patterns which solve the common problems. And we see like some of the best practices which need to be considered for building the effective microservice architecture. And in the final, we'll take some questions from the audience. So microservice architecture. So what is microservice architecture? So the traditional approach was building applications using monolith or modular monolith applications. So where we see a lot of issues like scaling application or technology login and improving the time to market, all those things are like drawbacks of the monolith application. So that is where the microservice architecture is gained importance, so that the business also uh, requires to improve the fast to market, and they want to also scale the applications independently based on their business requirements. So that is where the it becomes a de facto architecture for the most of the applications nowadays. So let's try to understand what is microservice architecture. So it's an architectural style that structure the application as a set of independently deployable, loosely coupled services. So in a monolith, we only have a single unit of application. Here we have a set of services which combinedly deliver a business value and business service, which serve all the business requirements. So it's not a single service, it's a group of services which solve the business problem. So how do we compose these services? Like services are built around the business capabilities, and each service is developed and deployed by the single autonomous team of 6 to 10 members. So this is also one important aspect, like how to compose and what is the size of the team. So there is a standard or recommendation from the architects, like the team should be small enough to fed by the two pizzas. Like it's a typically composed of 6 to 10 members. So this architecture enables to develop and deploy and scale independently to improve the time to market. So what is mean by time to market here? So means we can deliver our business solutions to the end customers as soon as possible they are ready. So that was not happening in the monolith application. The monolith application used to take a lot of time to build the application, test and deploy and deliver to the market. So that is where this is become a quite popular architecture. And one more benefit of this microservice architecture is, if one part of the system is broken or unavailable, the rest of the system is still unaffected and continues to function and fulfill all the business requirements of the end users. So as we have discussed, monolith has a lot of problems, and the microservice architecture is solving the problems. But microservice is a new architectural style, so it brings up the new challenges while building the microservices. So that is where we see some of the challenges. So some of the challenges I listed here are like how to decompose a big monolith into microservices, and how to discover the services, and how each service will talk to other service, and how do you manage the data, and how to ensure the consistency, how to handle distribution transactions, resilience, security, how to deploy, and observability. So these are all the common challenges come across building the microservice architecture. So as we seen, microservices have some challenges, but what are the solutions for that? So that is where we have the microservice patterns. So in general, patterns are doing things in effective way for the common problems that are occurring, and we solve those problems using all the best practices available and architectural recommendations. So microservices also have the microservice specific patterns. That is where we solve all those problems which we are come across building the microservice architecture. So high level, we can classify these patterns into some of the categories, like decomposition patterns, service discovery patterns, and data management patterns, and communication patterns, resilience patterns, and observability patterns. We'll try to discuss some of the patterns fall into these categories in this presentation. Okay, so before starting of the challenge, so I just followed a convention of picking up some of the challenges, specific challenges, and try to understand how to solve them and what kind of patterns that would help us to solve these problems. So let's start with the first set of challenges: how to break large functionality into multiple microservices, and how to ensure high cohesion contains strongly related functions, minimize the cross-team collaborations. These are the first set of challenges. So how we can solve this problem? Let's look at decomposition by business capability pattern can help to solve the discussed challenges. Because there is a big monolith or big functionality. We're trying to build the software product for that. So in order to use a microservice architecture, we need to divide the whole functionality into a set of independent functionalities to build the microservices. So these patterns talks about decomposed by the business capability. So what is mean by business capability? So business capability means a set of independent business functionality which serves one business purpose. So we need to identify what are the different business capabilities involved in the business model, and each business capability can be converted into a dedicated service. In this example, in the diagram, we have an insurance monolith. So insurance monolith is a big whole functionality which can be further divided into different independent business capabilities: sales, customer, complaints, marketing. So these each independent functionality is identified, and we can correctly scope with the proper business boundaries so that we can have a dedicated microservice for each of these business capabilities. So in this case, we can have a sales microservice, customer microservice, complaints microservice, and marketing microservice. So here, in order to develop microservice for a particular business capability, we need to have a dedicated teams for it. So how those teams should be composed? So these teams should be cross-functional, means the team can have diverse skill set people like developers, testers, DevOps engineers, and product owners, so that they all work together to build this business capability to build a software product for particular business needs. And these teams works autonomous, and they are organized around the business capabilities. And they only focus on delivering the technical solution for this business needs. It's not a pure technical solution, but it's a business value technical solution. This kind of pattern helps us to build a stable architecture because this is completely dependent upon the business capability. And here the services can be highly cohesive and loosely coupled. But highly cohesive means because we are already decomposed the services into different services based on the business capability. So all services will be holding their own closely related set of functionality. But the problem here is what is a way to identify the boundaries between the business capabilities. So the essential thing here is the SMEs or the product owner should have a sound knowledge in the business domain so that they can correctly decompose based on the business capability. So that is one of the essential part of using this pattern. This is one of the most used pattern while building the microservice architecture. Let's look at another pattern that also solves a similar problem. So here, as we've seen, the instance monolith is divided into multiple business capabilities. So as a microservice suggests, the service should be small enough to develop and deploy and scale independently. So in case, even after decomposing service by business capability, if each business service has huge set of functionality, and if that needs to be further broken down, and then that is where this subdomain pattern will come in the picture. So let's look at the sales business capability. So this business capability can be further break down into two different subdomains like purchasing and claims. So this identification is done using the domain-driven design principles. So where we can use or draw clear boundaries between the business capabilities and identify different subdomains so that the functionality exists in each subdomain can be closely related and easily connected with other services for their needs. So that is where this pattern helps to further break down microservice functionality into different subdomain related functionality. So here example, marketing also is a high level business capability. So this is further breakdown into campaigns, analytics, and reports. So here for each subdomain, we can build a separate microservice so that that can be independently build and scale. So here again, this is a one more challenge, like how to identify subdomains. So we need to make use of domain-driven principles and bounded context. So to identify the logical boundaries so that we can build the effective logical segregation of the business subdomain. So this is also suitable for monolith applications which already have the modularization in it, so that we can straight away use that logical boundaries to convert into microservice architecture. So how the team should be composed in this way? So the same, whatever we discussed in business capability decomposition, the team should be cross-functional, and the team will be having the diverse skill set people so that they can develop and build the applications based on the business value that they are delivering. Let's look at another set of challenges. Which development approach works well for building new system without modifying the existing one? And how to migrate the legacy monolithic application to microservice? So the strangler pattern is the solution or pattern that helps to solve discussed challenges. So we have a large monolith application or a big set of functionality we want to migrate to a microservice architecture. So this strangler pattern is inspired from the strangler victory. So this is the best strategy for migrating monolith application to microservices. And here we break the large application functionality of the legacy into a small business capabilities. So each business capability is again converted as a microservice in a phase manner, one at each time. In this diagram, if we look at, in the zeroth phase, we have a monolith. And the first phase, we extracted small set of functionality from the monolith and we converted into a one single microservice. In the next phase, we again took another chunk of functionality and build microservice 2, and so on. We'll keep repeat this thing until all the functionality of the monolith is converted into multiple microservices. At the end of this pattern implementation, all the functionality resides in the monolith is converted into set of all different microservice applications. So here we are converting or migrating the monolith application in phase manner. So each phase delivers the set of different functionality. This is an incremental approach to convert an existing monolith application into microservice architecture. But in practical, how this works? So is it something like until all the phases are completed and entire microservices architecture is built and deployed? Sometimes yes, but if it is a very big application, there is a possibility that both monolith application as well as microservice application coexist together for some time. In this case, let's say in the phase 2, I have a monolith application and I also have the 2 microservices. So we can deploy these two things together so that whatever the functionality that we built using microservices can serve the user request as soon as they are ready for production. So how these two things can be deployed together? So that is where we can use Strangler facade. So Strangler facade is a API layer which exposes both monolith and new microservices. So as soon as new microservices are built, we can route the traffic to the new microservices so that the new functionality that we build using microservice will serve the user request. And the functionality that is not there in the new microservices will be served from the monolith application. So there are some cases where the new microservices also can fail for some reason with respect to business functionality. If that is the case, the Strangler facade should also have a mechanism to switch back to the monolith in case the newly built microservices are not working as expected. But that shouldn't be the case most of the times. But we should have that backup plan ready with us. Yeah, at the end of the complete migration using strangler pattern and everything looks good, then we can simply decommission the monolith application and just we can proceed with the new set of microservices to serve the user request or the business functionality. Okay, let's look at another set of challenges. How to expose complex microservices system to communicate with clients, way to add security and other cross-cutting concerns in microservice. Okay, so it is talking about the communication and the cross-cutting concerns like security, way to add. Let's look at what pattern can help us to solve these challenges. API gateway pattern. So it's a single entry point for all backend services. So because if we don't have this single entry, so client should know about all microservices and what microservice is responsible for what kind of functionality. So that complexity is exposed to the client. So that is where this act as a middle layer between the client apps and backend microservices, and it hides all the complexity what we have in the microservice ecosystem. So this API gateway helps to expose a unified API interface so that client can easily access the microservice ecosystem with simplified API. And microservices use API gateway for various purposes. So there are many use cases where we can implement many features using API gateway. So we'll see some of them features. We can implement the microservice architecture, authentication and authorization as part of API gateway. So any request that is coming from the client can be processed through API gateway and verified the request is authenticated and authorized to send the request to a respective backend service. And we can also use it for routing and URL rewrite. So because my API gateway knows all the backend microservices, so when request comes in, it has a mechanism to identify that request is intended for which service. And sometimes we can also have the internal routes. So the client URLs and the internal client URLs could be different. So if that is the case, we can accept the external client URL and map it to the internal URL for the backend service. So that improves the most security aspect of the API routing. So that also can be done at the API gateway. So an API gateway can also support load balancing and caching responses. So if we are using a frequently querying some particular operations using some APIs, so we can cache those APIs responses using the internal cache systems of API gateway, or we can integrate with the external cache systems like Redis, so that we can improve the API response performance. We can also implement rate limiting so that our system can be more resilient and robust, because the attackers can unwantedly they can send bulk traffic into the system to crash our microservices. So we can also set up some rules to rate limit the requests coming from the a particular host or particular domain. And protocol request translation. And the client app send the request to API gateway, right? API gateway can additionally add and delete and customize the request information like headers and send it back to the backend services. Sometimes we also require to use the protocol conversion. Suppose in microservice system, I have a like kind of SOAP service. Suppose let's say service A is a SOAP service, but the client apps doesn't really need to worry about the SOAP. They can still use the REST. The API gateway can responsible to convert that REST API to a SOAP service and make a call to service A. And once service A is responded back with a response, and that response again converted into the appropriate format to the client app. So this act as a like a kind of translator in that case. And API gateway also supports logging and monitoring and tracing information. So it can send the informations of request and response and track those all the details of performance and send it back to the backend appropriate logging and monitoring and tracing software components. The final, we also can enforce some resiliency at the API gateway. We can apply some retries over there before failing the request. And we can also enforce circuit breaker functionality in the API gateway. So there are many functionalities can support at the API gateway. And API gateway also sometimes used for exposing the legacy services. Suppose in case if I don't want to convert my service, legacy service into microservice immediately, so I can make use of API gateway to expose my legacy application using modern API like REST API or GraphQL API. Yeah, these are all the things that we can expect from the API gateway to support. And there are different kinds of toolkits exist to implement this pattern. We can use Azure API Gateway or AWS API Gateway, APG. We can have the Spring Cloud Gateway and Joule. We can implement programmatically. We can also utilize the cloud components. But here there is a problem. Like we are doing a lot many things at the API Gateway. So what if your API Gateway goes down? So it's become a single point of failure. So we need to make sure this API gateway is highly available so that our system is always up and running. Let's look at another set of challenges. Overfetching or underfetching data from backend services for frontends. Code or integration complexity in front-end application to aggregate backend service data. Too many API calls, network round trips, and performance for front-end application. So this is dealing with the front-end client application integration with the microservice architecture. So backend for front-end pattern is a pattern that helps all the previously discussed challenges. So what is the backend for front-end? So it's an abstract layer that hides the complexity of the backend services for front-end clients. In this diagram, if you look at, it was bit looking same as the previous diagram that we seen for the API gateway. So in place of API gateway, we are seeing the BFF application here. So what is this BFF application? It's an intermediate backend service which sits between clients, apps, and backend services. So what is the essence of adding this new service here? Let's look at the case. Suppose a web application needs some data from the backend services. So backend services are typically built using a REST API or gRPC. So they provide some response. So probably that response that is coming from the backend service might not be completely used by the client apps like web or mobile. Maybe that is where we are calling it as overfetching the data. So probably I need only 3 attributes in the response. My response may be having the 10 attributes, which is unnecessary. That may increase the traffic load and the serialization time and deceleration time. So that is where I want to make sure, why should I build a response for the client needs? So that is why we are building the BFF layer. It's a different intermediate backend service, which actually make a backend call, and it will get the data from the backend services, and it only sends the request with the required data format or data attributes to the specific client. In this case, we have 2 clients, web and mobile. So web and mobile can have their own dedicated backend for front-end applications, which expose a simplified client-specific API. They expose the data what their client needs. The mobile needs some data. The mobile app BFF only sends the data that is required from the mobile. So since the client apps could be different, web, mobile, desktop, or any ERP integration, if that is the case, all the clients request different kind of data. So we need to have a separate dedicated BFF service for each of these clients so that the client application is very simple to integrate with the backend services with a single call. Otherwise, what happens if I need data from multiple services, then a client application will end up making multiple calls to the backend service and aggregate that information in the client side and render in the UI page. So that is not really required, and that makes UI integration and code very complicated. So this BFF pattern would help to have a cleaner code and integration with the client apps. So the BFF pattern enforces to have each client to have a separate backend services. So we can also treat this BFF service as another variant of API gateway. In practical, BFF services deployed in conjunction with the API gateway. So we will build a separate API gateway for mobile app and a separate API gateway for web app. If there are any other client apps like ERP or desktop, we'll be having separate deployments for that. So typically these BFF services are built using REST or GraphQL or gRPC. So this service also responsible to aggregate the data from the different services for cleaner integration of the front-end applications. Yeah, let's look at next set of challenges. How clients knows backend services to connect. How backend services knows each other to make inter-service communication. Okay, so this is talking about how client will know where is my service running and how to connect with it. So that is where the server-side discovery pattern will come in the picture. Since in the microservice architecture, every service is deployed as a multiple instances because we need scalability. It's not like one service instance will always serve the request. Based on the traffic and based on the high availability of the system, we should have a multiple instance of the service to be deployed. If that is the case, how client would know and where the service instance is running and what happens if that service instance goes down. So all the details client should worry. So that complexity is not necessary to expose the client. So that is where we can use server-side discovery pattern. So in this, services that are running in the microservice ecosystem register themselves with the service registry or discovery service. If you look at this diagram, so there are service A instances, there are 4 instances are there registered with the service registry. And the service client is faced with the load balancer, and the load balancer is accept the service client request and it look up the service registry and pick up the healthy instance which is free to accept the request and send the request to the that respective backend service instance and fulfill the request. So what happens if any of the service goes down? So service registries keep track with the all active running services in the registry. And by any chance, if service instances goes down or unhealthy, the registry will track those services through their health check and heartbeat. And if they are unavailable to accept any request, those will be automatically unregistered in the service registry so that load balancer won't be finding that crashed instance for routing the request to the backend services. So this enables highly scalable application in the microservice architecture and also hides the complexity of how many instances are running, how application is scaled, how instances are running. All those are completely hidden to the service client. So this is one of the widely used pattern, the microservice architecture. There is another pattern. Yeah. What is a toolkit that we can use to implement the server-side discovery pattern? So we can use Eureka and HashiCorp Console's discovery service, and we can also use Kubernetes service in a containerized applications with DNS resolution. And so these are the standard practice to implement the server-side discovery pattern. So there is another pattern in a similar lines, like client-side discovery. So that where we implement the discovery at the client side. So most of the times that is not widely used, but that is also based on the needs, we can programmatically implement the client-side discovery. Let's look at another set of challenges. Microservices can become unavailable at any time. How to send updates to other microservices to perform business transactions during their unavailability. Yeah, as we've seen, the microservice architecture is not strongly consistent. And it's a set of microservices, and we never know like which services goes down and when it will come back. So if that is a case, how do we make effective communication and how to ensure our data is consistent between the microservices? Event-driven architecture pattern. So these patterns solve the challenges that we discussed. What is mean by the event-driven architecture? First of all, we try to understand what is event. Event is a representation of state change in the microservice. That means a user send a request to change the data, change the state of the application by sending create or update or delete request. So that data change is captured in the database and storing in the different kinds of database. And we also want to propagate that change to the different microservices. If you look at this diagram, in e-commerce applications, so here we have a different set of microservice: payments, checkout, delivery, inventory, and invoices. So once the payment is completed, the payment service is responsible to store the payment completion status in its own local database and communicate that information to other microservices, saying that the payment is completed. So it publishes a message to the message broker or event broker. That message will be listened by the checkout process and it will update its own database upon payment complete and again emit one more event. So this communication happens asynchronously using the message brokers. So in case after publishing the message by the checkout service, if the delivery service is down, so delivery service can consume this message as soon as it is available. It is not necessary that delivery service should be always up and running to process this message. So likewise, this event-driven architecture is communicated using asynchronous messaging and publish subscribe pattern. This helps to achieve system to be more scalable and highly available. Yeah, so here, as we see here, like messages are getting published and messages are getting consumed by the different services. So each consumer will update their status upon receiving the message. So it's not necessary that every message should be consumed by the every services. Like only interested services that really need to process and update their databases, they only can consider. Suppose the payment service publish the purchase complete. This is not listened by the delivery, inventory, invoice, because that is may not be a business functionality to listen to that message and process it. So this architecture helps to build the loosely coupled services in the microservice architecture. And here we don't be getting the strongly consistent behavior in terms of data management, because this architecture is an event-driven architecture and we are sending the message asynchronous to the message broker, and services can be unavailable at any point of time. They can only consume and process the message their own pace. So that is why the data is eventually consistent. So how to implement this event-driven architecture in general? We can use any messaging brokers like Kafka or Azure Event Hubs, GCP PubSub, AWS SQS, and RabbitMQ. So we look at another set of challenges: writing a data atomically to database and messaging systems. What if writing to a messaging system fails once database operation is successful? How to ensure data consistency in event-driven architecture with database and messaging systems? Let's look at this diagram carefully. transactional message send failure. My client application is creating an order and the transaction is started and order service stored the insert order event in the database. But this event has to be sent to the other systems using the event-driven architecture. What if this event gets failed while publishing to the messaging bus or event broker? We store that state in the database, but we are unable to send this message to the message broker to send it to the different service using the event-driven architecture. So this is exactly the common problem that we see in most of the microservice architecture. So in general, people may attempt to write a rollback transaction in the database. So they revert the transaction that is saved in the database. Probably that is a ideal solution for some reason, but most of the times, no. But how to solve this problem? Transactional outbox pattern. So this is an ideal database backed service pattern. So where we store the data in both tables. So we write the data into the entity table as well as the outbox table. So outbox table is the additional table where we capture the event that we are trying to send to the message broker. And the entity table is the data that we are trying to store in the database upon the state change in the microservice. But here we are storing the data into the two different tables, data and event that we are trying to send. We have to store this data in the database tables in the same transaction. So most appropriate to save this data into two different tables using the same transaction is possible in RDBMS databases. So atomically, we can write the data, and there is a separate process which will listen to the outbox table, and it will read the data from the outbox table, which is an event that we are trying to send to the messaging queue, and it will send that message to messaging queue and delete that message if needed, or else it is marked as a processed, so that we can ensure that outbox table event is sent to the message queue. So what if the case that we discussed, message queue is down? So the separated process, the publisher will re-attempt to send it to the message broker, and if it is unable to send it, again report to the database outbox table, and it will try to resend it to the message topic. This will be keep continued until that message is posted to the message queue. So this way we won't be losing that message, and we ensure the data consistency across the database and the messaging queue. Whatever the message that we send to the messaging queue will be consumed by the interested consumers. So this pattern can be implemented in multiple ways. So one approach is like a polling publisher that we discussed. The publisher will just poll outbox table and read the message and send it to the messaging topic. Or else we can use the change data capture mechanism. Automatically, this can push the message to the message queue as soon as the entry is stored in the outbox table. So this is where we use log tailing pattern. So some of the databases support this log tailing. So like MySQL and Postgres, they have the log tailing approach. They can read the transaction log. So based on that, they can understand what is changed in the table, and that data will be emitted as an event to the message topic. So this is quite complex to implement. So we have a tools like a Debezium, which provides the Kafka connectors. So that will be connected with the databases, and it will push the data to the Kafka. So this is one of the most widely used pattern in the event-driven architecture to ensure the data consistency, to send and store the data, the database and messaging systems. Let's discuss another set of problems. Separate performance SLAs for read and write operations. Poor read performance due to complex giants or aggregating multiple service data. Read and write performance is not optimal due to same data model. We'll try to understand what exactly this problem. Let's take an example in e-commerce. So e-commerce site, there are many users are trying to view the product catalog page, and they are trying to see the information of what is that product, what is the quantity available, and what is the price of it, what is the discount applicable for it. But when you look at the rights part of the same functionality, so the database administrator or application administrator will just write the data to show the data to the end user. So writes are minimal in this case, but reads are heavy because every user trying to look at the catalog to purchase the product. So if this is a case, we have a different read and write performance requirements. So there are millions of users are trying to buy an item at the same time. So there are many requests are coming into the system. So our system need to be read effective to serve the response on defined performance SLAs. If that is the case, if you are going with the same database model for both reads and write, it may be a difficult task to show all the necessary details to end user when they are requesting. So that is where this command query responsibility segregation pattern come in the picture. So this is focus on data model optimization, and it works on segregating the read and write models using commands and queries, separate data models, which is used for improving the read write performances. So most typically, if we see the same case, e-commerce product catalog page, the product information comes from the catalog service, and the quantity information comes from the inventory service, and the price and discounts come from the discount service. So this is a aggregated data from the different services. So if you are querying this data on demand when user request and fetching this data from 3 different services or 3 different tables by joining or aggregating this data would be very costly. So that is why what we can do is we can build a separate denormalized model of these 3 pieces of information and store it in a separate read database so that that can be read as a single document when the user is queried for it. So that is where the read performance is optimized with this CQRS pattern. So most likely, this pattern helps to solve this performance problems by maintaining 2 different kinds of databases, one for write, one for read. And at the same time, the query model and the command model also would be different. So this is basically helps to avoid unnecessary aggregations during query time or avoiding the complex query giants. In general, CQRS is often used with event sourcing. So most of the times, CQRS and event sourcing are implemented together in practical microservice architecture. So event sourcing is another pattern. High level, I will try to explain that. Event sourcing is a pattern where we store the application state in a sequence of events in the database, and we can replay or restore the previous state as and when it is needed. An example, suppose a user is given with some moderate permission today. Tomorrow, someone has changed that moderation permission to admin permission, which was not expected. But we want to roll back that user permission to the moderator. We can just replay all the events of permission changes to the today's date so that he can get the state of what we captured today. So that is how we can use the event sourcing along with the CQRS pattern. How can we implement CQRS pattern? This is a quite complex pattern to implement it. It's not easy. And there is one more challenge involved here is how this read and write database are in sync. Because I'm writing to one database, I'm trying to read from another database. How read and writes are in sync. So we need to make sure we need to have a separate process to sync data between the write database and read database. But this only ensures the eventual consistency because we are going to use the event-driven architecture or any other the polling mechanism to sync the data between the write and read databases. So that is how this gets complicated and only achieves the eventual consistency. We can use Kafka and event-driven architecture, and there is a framework called Axon framework. It is a like a framework to support CQRS pattern in a very easy manner by hiding a lot of complex things. Let's look at another set of challenges. How to handle failures and timeouts in service communication using API calls. How to handle cascading effect of failures in the event of microservice failures or unavailability. How to make system more resilient during failures. So what is meant by cascading failure? If you look at this diagram, so there are 4 microservices trying to connect each other to get the response from each service and compose the response to the end user. So microservice A is trying to call service B, and service B is trying to call service C, service D is trying to call service C. What happens if service D is unavailable or crashed or unable to provide the response back to service C? So what happens if service D is failed, then service C also would fail because it was expecting a response from service D. Similarly, this error propagation will happen till all the way to the service A. So this service A simply written a error back to the requester. So which is called a cascading failure. The failure which exists at service D caused to failure every service like C, B, A. The request entirely become failure. So this is sometimes accepted, but most of the times this might give a bad user experience. So how to solve this problem? So if you look at right side of the diagram, so we need to make use of circuit breaker design pattern. So where we can gracefully handle the exceptions of the microservices and provide the proper fallback responses so that we can make sure the services which are in the stack of API calls can get succeeded with the fallback responses. So in this case, service D got failed, but service D is still passed because the service D failure resulted into a fallback response, and that is eventually propagated till all the way to service A, and service A served a request with fallback response. So this is where the circuit breaker pattern helps to avoid these cascading failures. We'll try to understand what is the circuit breaker pattern and explore how it works. What is circuit breaker design pattern? Circuit breaker design pattern helps to avoid cascading failures. So it's a software component which sits between client and microservice, which monitors the remote API calls for failures. If you look at this diagram here, we have a client and microservices. So there are a series of like steps performed during different scenarios. When the client send a request, in the first case, the client send a request, and if everything goes fine and microservice is ready to serve the request, the circuit breaker listen to that API call and it process request and response. This is a happy case. Suppose the client is sending a request to microservice, but it is failed. But this circuit breaker component is monitoring this failure, and it will continue to send the further request to that service until the configured threshold value of fail count is reached. Suppose I configured fail count of 5. If 5 times the microservice API calls are failed, then I will take an action. So until that time, it will keep allow the request to the microservice. So what happens if the threshold that we configured is exhausted, like 5 is reached? So if that is the case, the circuit breaker open the circuit and it doesn't allow the further request to the microservice, because the microservice understood, circuit breaker understood that microservice unavailable, and there is no pointing into sending the request to that microservice. So in that case, as soon as the client request comes in, the circuit breaker immediately return the error. It won't translate that API call to microservice. So how long this circuit will be open? So there will be a timeout period configured for it. After the timeout period, it will try to check whether that particular failed microservice is recovered or not. If it is recovered, and you can able to support the API calls. Then it will try to check, and it will open the state to off open, and then it will try to send some limited number of requests to microservice to check whether those can be successful or not. The circuit breaker, if it finds the limited number of API calls are getting success, then it will close a microservice. But what happens if still microservice is unavailable and it is unable to send the response back? Then again, it will open the circuit. This will keep continue. So high level, this circuit breaker pattern is like kind of gateway to send the request to the microservice, and it will keep track of the failures of the microservices. And it ensures if there are failures exist, it gracefully handle those exceptions and provide the fallback responses for the clients, so that the effect of the failures would be gracefully handled and improve the better user experience. So what are the tools that we can use to implement this circuit breaker design pattern? So as we discussed in API gateway pattern, we can enforce circuit design pattern in the API gateways like Azure API. We can define the resilience patterns over there. And instead of having the separate programmatical implementation, we can go with the API gateway to implement this thing. We can also use service mesh. This is a advanced concept where we can also use a circuit breaker design pattern. And programmatically, we can use the resilient 4J for the Java Spring-based applications. So overall, the circuit breaker design pattern is a intelligent pattern to understand the service failures and route the request to the appropriate fallback responses. And it also emit the metrics of request response failures to monitor and trace the event failures. Let's look at another set of challenges. So traditional transaction cannot work for microservice architecture. How to handle transactions span across multiple business contexts or services. So basically, this is dealing with the how transaction can be performed in the microservice architecture. Let's try to understand how transactions can be handled in microservice architecture. Before this, like in the monolithic application, how transactions are handled. Because in the monolithic applications, everything is within the same application. So there is no network call, and most of the times we only deal with a single unit of application and a single database, right? So we can use ACID properties for the relational databases, and we can achieve the transactionality over there. And there is some sort of like a distributed transaction also required if you use a multiple data stores in monolith applications, like sending message to some queue and storing the data. There we can use a two-phase commit kind of protocol to support the distributed transactions. But can we use the same things in the microservice architecture? So is two-phase commit can help here? No. So it cannot work in microservice architecture. So that is where we have a Saga pattern. So Saga pattern is basically used for the distributed transactions. So the Saga pattern is basically a sequence of local transactions. And more specifically, we are talking about the choreography-based Saga pattern. The choreography-based Saga pattern is a event-based pattern, and it's not centrally not coordinated. All the logic of processing these transactions is resides in the each of the microservices, and the every service upon state change, it updates its local transaction and save the data in the database and publish the state change event to the downstream applications. So in this case, order service is created an order and save the order status in the database and send an event to a message broker saying that order is created. And the payment service is going to listen this order created event and updates its own local transaction. And once that payment is done, and it send a ordered build event, so that that order build event can be listened by the event service, and event service can do its own processing and update its local status. And if inventory is available and everything goes fine, then it will send an event order prepared. So once the order is prepared, that this event is interested by the delivery service, this will be listened by the delivery service, and process according to the delivery times and update the status and send the event back to message broker. Order is delivered. This all order created, built, prepared, delivered. Every event can be listened by the order service and update the latest order status. So if we look at closely this diagram, there is a predefined steps for each microservice. If order service sending order created and payment service only interested to listen order created and inventory service is only interested to listen order build. Likewise, all services are interested in certain events to update their local transactions. So this is a predefined steps of uh, actions for performing the business transactions in the different microservices. So that is where it's a set of actions for doing their local transactions. So what happens if any failure happens in this case? The one we looked at is a happy case. So in the failure case, in the bottom diagram, so order services create and updated its database and it emitted order created event. So this is listened by the payment service and the payment has been done and it is sent another event, order is billed. So the even inventory service is listen order build event and it is trying to check the inventory, but it found that our item or product is out of stack. So it cannot proceed. So it cannot send order is prepared. So instead it is sending out of stack event. So out of stack event is listened by the payment service. So as I mentioned, so every service is defined to be processed certain events. Then the first case, it was listening only order created. In the failure case, the payment service is also responsible to listen out of stock event. In case of item is not available, the payment should be refunded to the end user. So that is where this out of stock event is listened by the payment service and initiate the payment refund transaction. And all these events can be listened by the order service to update the latest status of the order. So this way we can make use of the event-driven architecture and perform all local transaction across the different services to fulfill the business transaction which span across the multiple services. So we can only achieve the eventual consistency in this case. And as we seen, like if in this architecture, if any of the transaction is failed, we are rolling back all the transactions that were previously done in the system. In this case, the transaction that we done was the payment is successful, that we were reverting it. So that is, we are calling it as a compensation transaction to roll back the previously successfully executed transactions. So in all the cases are successful, then we are updating the latest state. If any of the transaction is failed, then we are reverting all the transactions that are done during this total business transaction. So this is also widely used pattern, and there's a challenge in implement this pattern. And because if there are too many microservices, we end up having too many messages, and this looks complex and hard to understand, and maybe hard to debug as well. So that is where like we need to enough careful to use this pattern. And we also choose this pattern if it is really required to use it. Otherwise, we can look for the alternate solutions. So how can we implement this pattern? We can make use of event-driven architecture, and there is a framework called Action and Eventuate. These are the two frameworks which simplifies the Saga pattern implementation. So if we want to go with our own implementation, this is going to be very complex. The next pattern that solves the business transactions is Saga pattern. It is an orchestrate-based pattern. So unlike choreograph-based transaction, it is a kind of orchestrator-based Saga pattern. So here there is a central coordinator or orchestrator. He manages all the transactions that were happening in the business transactions spanned across the services. So the Saga orchestrator is responsible for listening to all events, and he makes sure sending all the commands, what action to be performed by each service, and he is responsible to roll back in case any failures happens in the transaction flow. So in general, Saga orchestrator send a command message to Saga participants to perform the particular operation, and each participant or each service will do its own local transaction and send replay back to the orchestrator using the different channel. If you look at this example, order service sending a create order command. Command is nothing but a request which expects some state change in the service. So orchestrator receive a command, and it is sending a payment command. Just do this payment, and that is instructing payment service to do the payment. The payment service is listen this command and process the payment. Once it is successful, it will send a reply back to message broker, the order Saga reply channel that is listened by the orchestrator. Orchestrator listen to that success message of payment, and he'll understand the payment is successful, and next he issue the another command to inventory command. So that inventory command will be listened by the event service. That event service will process the inventory check, and if everything goes fine and inventory is available, it will send a replay back to order Saga to listen by the orchestrator. So orchestrator understand that inventory is also available. So now I need to send another command to delivery service saying delivery command. So delivery service will again listen to that message, and it will process the delivery and send back the reply to order Saga reply to listen by the orchestrator. Again, orchestrator listen to that message and update the latest order status. So is centrally coordinating all the actions and listening the response of each service and updating the status. It is centrally coordinated. So what happens in case of failure? Sorry. So in case of failure, in the same example, order service again sending a create order command. So orchestrator listened to that command and issued a payment command. The payment is done by the payment service, and it is sending a success reply to the orchestrator using order Saga reply. So we updated status to the payment is success. Now again he sent it another command to inventory saying inventory command. But in this case, the inventory service is saying that I don't have item out of stack. It is sending out of stack reply to orchestrator using the order Saga reply channel. So order orchestrator understood that inventory is not available. We cannot proceed with the transaction. We need to roll back the transaction that we have done previously for this whole business transaction. So that is why it will send another command. This is a refund command. The refund command is interested to listen by the payment service. The payment service understand that something is went wrong. I need to roll back the change that I made for this business transaction. So it will compensate the transaction, and it will revert the payment and refund to the client. So again, that will be sent to the order Saga reply, and orchestrator will update the status that the payment refund is initiated. So that is how the Saga pattern in orchestrator way, it will perform all successful transaction as well as the failure cases. And the failure cases also handled in a similar way what we have seen in the choreography based. All the transactions that are done previously will be rolled back using the compensation transaction. Here, refund command is a compensation transaction that is executed by the payment service. Okay, and this pattern is also like implemented in most of the architectures where the business use case is minimal and we only have a set of limited services. This is easy to implement, and but if there are too many microservice and too many action need to be performed as part of the Saga pattern, then maybe this is not a like optimal way of doing it, because everything is centralized at the order orchestrator. So if our orchestrator goes down, then everything will goes down. So we need to also wisely choose a pattern which one is suitable for our business needs. So in practical, like people will use a hybrid approach like orchestration and as well as the choreograph based. That works well most of the cases. So like the tools, whatever we seen in orchestration, like event choreograph based, we can use the same kind of frameworks like eventuate and action framework to implement this orchestrated based saga pattern. Yeah. Now coming to the best practices, I think we are done with all the challenges and the patterns that I'm trying to cover. Now we look at some best practices. So we've seen many challenges and what kind of patterns helps to solve these issues. There are many other challenges as well. Within the time is concerned, I try to cover the most frequently occurring challenges and most widely used patterns in this presentation. So there are other patterns as well, like security patterns and observability patterns. Uh, Let me briefly tell about security and observability patterns as well. Security patterns, like how the security is handled in the microservices and where it is handled. As we know, like those can be handled in at an API gateway, and we can use security access tokens to authenticate and authorize microservices. And coming to the observability patterns, unlike monolith application, we cannot have the logs at one place. So each service can have logs at its own place. And in order to troubleshoot any business transaction or business user request, so we need to combine all those logs together at one place, and we need to search through the logs for troubleshooting and debugging the issues. And we also need to monitor and health check the microservices. So for that, we need to use open telemetry or open tracing and Zipkin, and we can use cloud solutions like CloudWatch, Azure Monitor, Datadog kind of solution will help us to enforce this observability and monitor the microservice ecosystem. Coming to the best practices, so we have seen a lot of problems and patterns. So we understood already, like design patterns helps to solve the problems. So that is where microservice design patterns help to avoid complexity at scale. Maybe in a small scale applications, we might not see big problems even if you don't use some patterns. But in a bigger applications, definitely we need patterns to avoid the complexity. So that helps us to solve the most of the problems that we encounter in the application development. And we also need to choose the communication styles for the business requirements and the scalability and performance needs. So otherwise, the performance won't be gained with improper architecture. And there is one more big challenge in microservices, like a distributed transaction. So as a best practice, we need to minimize the distributed transactions for better data consistency. So this is directly related to the decomposition. Suppose if we are unable to decompose uh, services into proper bounded context, then we might end up doing a lot of service calls to serve the business data. So that eventually leads to the lot of distributed transactions. So if we have too many distributed transactions in our system, then the data, the consistency goes down. So that is why we need to minimize the distributed transactions for better scalable, better data consistency. So also we need to enforce security and observability in order to secure microservices and troubleshoot using the logs and uh, track the request response time using tracing and understand the metrics for the service failures and health checks. So this is also very much important to enforce in the microservice ecosystem. And last but not least, this is very much important. We need to document the microservices. So what is meant by document here? We need to document all the APIs of each microservice and how the microservice is designed and what are the dependencies that we have within the microservice, so that the teams can easily refer this documentation to minimize the team collaboration. Because the microservice ecosystem is huge and there could be a number of services. If we never know what service is responsible for what kind of business functionality, it is hard to integrate between different services. So that is where this documentation help us to build the effective collaboration between the teams. Yeah, I think that's all. So we are almost done with all the things that plan to discuss. So probably covered most important patterns. We are left with some other patterns also. If possible, try to cover that rest of the patterns in upcoming sessions. Uh, and let's take questions from audience. Any questions?
Hello,
Hi,
Chandra.
hi, Prithvi.
Can we implement the saga design pattern inside the event-driven design pattern, because saga design patterns is only for the consistency?
Yeah, Saga design patterns can be implemented using blocking and non-blocking approach. Like blocking means Saga can be used in order to make a synchronous communication with the services and compose a response, right? And the most of the times we use event-driven architecture. So event-driven architecture is a key architecture for all these patterns. So most of the patterns work based on the event-driven architecture only. So because as we seen in the Saga pattern, we are sending the events or commands to the message broker. So we are sending the events or commands to the message broker means it's an event-driven architecture. Because you are not expecting every services to be available at any given point of time, because we never know like when they goes down. So we need to wisely choose how to implement it. If some cases you need to perform some operations synchronously, if that is the case, you need to make a API call to get the response from the service instead of putting the message in the queue and wait for the service to consume and replay back to you. So that is where like in real scenarios, we use hybrid approach. We use choreography based, orchestration based, and we also make some synchronous by making API calls. So that's all depends on the use case, how your request want to be fulfilled.
Okay. And one more question is like, how can we ensure the old component and the modernized components integration in Strangler design pattern?
Sorry, come again. How to?
How to ensure the integration of the old and the modernized components?
Yes. So that is where like I mentioned like strangler facade is required. So because you already have a off-build microservice system and you have a full monolith application. So you need to expose these two different ecosystems using an additional layer called strangler facade. That actually a front controller for the end users. So end users will talk to the strangler facade. So that will route request based on the functionality that you have in monolith as well as the microservice system. If the microservice system doesn't have that functionality, that request should be routed to the monolith. Even some cases, if the newly built microservices doesn't working properly, then automatically we can switch back to the monolith for the subsequent request who are requesting the same functionality again. So that we can use some feature flags kind of things. If something is going wrong with the microservice, just you can flip that to route to that monolith so that it can work as before.
Thank you.
Any other questions?
Chandra, Bharat here.
Hi, Bharat.
Yeah, so in case of the user base or the customer base, it is often the situation is like we should also have the basic minimal information available for the each microservice to tag to the customer or tag to the user. So eventually, if the business grows, then the data of user base also will grow. So the point here is at some phase, each service has to be independent, and there has to be definitely the inter calls between the services also should be handled a better way, so that overall the ecosystem of microservices still maintained irrespective of the growing business, especially with the user base, right? So what do you suggest, like what will be the best to handle this use case where user base is growing day by day in the business?
Okay. So if I understand your question correctly, you're talking about the microservice communication and how effectively you process a message if the huge load, huge request is coming in, right? So we can make use of event-driven architecture. Event, sorry.
No,
Yeah,
go ahead.
we can make use of event-driven architecture. So this message brokers are helps to scale our systems for the asynchronous processes, and we can have the like make use of this Kafka kind of frameworks or libraries to serve the like high volume of messages, and we can deploy like high number of consumers to process the request in near real time. But if in case of like it's a synchronous processing is we need to deploy like multiple services to handle the huge traffic.
Okay, thank you.
Any other questions from anybody? We have one more question in chat. Yeah, let me see the chart. Okay, so the question here from Tirtha, how do we decide to split monolith into microservices? As recently, few Amazon Prime services has switched from microservices to monolith due to cost issues. So what about this? Yeah, so this is a good question, and people like they're confused with this the architecture change from the Amazon Prime. It's not the case they are suggesting we need to move to the monolith. Yes, that worked well for them, but it's not always true for everybody. But we need to consider a lot of factors whether we need to go with the monolith or microservice. So the Martin Flowers says, if you really start building a microservice architecture from the beginning, you end up lot of having problems. You start with monolith or modular monolith. Eventually, you convert that application into microservice. If there is a really need of using microservice and where you are getting the benefit out of that. So even Sam Newman also suggests the same thing. If you really find the benefits of using the microservice architecture, then you use it. So we need to be enough intelligent to understand what is the best architecture style that we can go with. So in general, people also might tempted to use the microservice architecture for every single thing. Like they end up creating too many small microservices. So if you have too many microservice architectures in the system, right? So then that eventually increase a lot of network traffic, and you also lose your data consistency. Your data consistency will be less, or you having eventual consistency, even for the cases where you need strong consistency. And choosing between the monolith and microservice is also important in two aspects. One is scaling. So what is the functionality that you want to scale? So if you want really that functionality to be scaled in very high, so that has to be definitely a microservice. And another factor, very important factor, is data consistency. Suppose your business needs very strong consistency. If that is the case, if you are going with that microservice and with the Saga pattern and distributed transactions, then that's not a good idea. So whatever the functionality that you want to like ensure the strong consistency, that has to be reside entire thing in a single service. So that is where we also have a decomposition for transaction. There is another pattern called decomposed by the transaction. So instead of having your whole business transaction across the multiple services, you can club the entire functionality that is spread across the 4 services into a single service and do a local transaction. Instead of having 4 transactions, club them into a single application and have a local transaction so that you can achieve the strong consistency. And one more thing, like coming to the Amazon Prime thing. So we can build and split the microservice in any way, but what are we achieving and what are we losing? These are the 2 things also we need to consider. So you are splitting application into too many microservices, then you need to have a separate pipelines, deployments, and monitoring tools, and everything is required. So that also cost more. So that is where like we have to be very careful in decomposing the microservices. Decomposing the microservices is one of the biggest challenge. If you are really slicing the microservice in proper way, then you will be definitely having the well architected microservice application. Hope this is clear.
Yeah, thanks.
Yeah, there's another question. What should be ideal size for microservices in terms of memory and processing units allocated to microservice? This is a tricky question. The size, I think I don't know like what is mean by size. So we generally follow like domain driven principles. And as I mentioned, any independently developed and deployable business functionality by a set of 6 to 10 people can be ideal to be considered as a single microservice. So this in terms of memory and processing units are depends. Applications are different in nature. Some applications are CPU intensive, some applications are IO intensive. So based on that, the heap memory or the CPU or processing units need to be allocated. That is purely dependent on the application nature. Any other questions? So I also wanted to highlight one more point. So it's a monolith application can still be considered for our architecture. It's not like the monolith is gone and only the microservice. Because the monolithic application also has its own pros. Because the monolithic application ensures the strong consistency. Some of the business applications still need that. So that is where we need to consider the monoliths. And as I mentioned before, the microservices has their own strengths and they also have the lot of problems as well, because we end up having a lot of tools to support the microservices. Microservice architecture is not as simple as monolith. So we need to have a lot of things, tracing, monitoring, troubleshooting, and managing the transaction. These are all involved a lot of complexity. So there are a lot of tools to solve these problems, but we need to really understand that much complexity is really required for my business requirement or not. If yes, we can go. If it is not, we can go with the modular monolith. So modular monolith also another architectural style where we can divide the business functionality as a separate modules and deploy it as a single unit, and which allow us to manage things more organized way and we can easily test it and easily deploy it.
Chandra, one more question. Sorry at this time.
Yeah, who is this?
Sudhakar.
Sudhakar.
So Chandra, when we talk about the microservices, we only say that it's in the modern applications which we can see microservice implementations. But do we still stand this microservice architecture for legacy systems as well?
Sorry, I lost you, Sudhakar. Come again.
Can we still implement these microservice architecture design patterns in the legacy system as well?
Answer is no, because we don't have the challenges over there. Because it's a complete the paradigm change, right? Architecture style is different. So because if we take Saga, do you need really Saga in the monolith? No. Why you need Saga? Because your business functionality is spread across different services. You need to manage the data consistency and the transaction in different services. But in case of monolith, everything resides in a single application. You are not going to do changes in different databases. You are going to do change in single database. Right? And communication patterns. So the communication patterns, do you need any communication patterns here? Event-driven, async architecture, do you need anything? No, because you can invoke just internal methods within the application that will serve the communication between the different modules. So these are all the new things that come up when you migrate your architecture into microservice. So that is where these patterns help us to solve those problems effectively.
Thank you, Chandra.
Any other questions from anybody? Yeah, if you have any questions, just feel free to ask. Still, we have some time. Okay, I take it as no. If you still have any questions, please feel free to ping in our YouTube channel so that we try to answer the questions. Thank you all for attending the session.
Yes. Yeah. Thank you, Chandra. It was a really great session. It was very insightful, and I think everybody was very interested and enjoyed every part of it. We will be conducting more series, more events under the Dynamic Talk series. Please stay tuned to our social channels. You can follow us on Facebook. You can also subscribe to us on LinkedIn. Please do follow our updates for more, and we will be back soon with more content. Thank you, guys.